Just so you guys are aware what a distribution is. It's, again, kind of like a histogram, but connected by a continuous function. And we are looking at the normal. The normal distribution is a continuous curve. And one of the things that we're going to be looking at is probabilities or percentages of the data that's within a particular range as area under that curve. Okay? And that's what we'll explain more tomorrow. Today what we're going to look at are the means, and then using the standard deviation to approximate certain percentages of the data. Tomorrow we'll look at exact ranges that aren't right on those different intervals that we'll look at today. Okay, so before we move further, it's 9:29, so if you need to go, I'll let you guys go, and then those who are here will continue on. Okay.
Don't die.
He's so cool. We'll come up and then you're gonna regret it.
Okay. I won't be talking to you straight on air. I'm inviting you guys to my school to talk to my entire class.
And then you have no fun in your life. Bye.
All right. All right. So looking here, let's take a quick look at notation, because notation is going to be real important that you understand. Guys, the notation can be very confusing, but if you learn it well as we go, then it's not too hard, okay? What we're talking about is a random variable, and what that means is that we're just picking a value at random, okay? We use a capital letter X for that. It may be hard to recognize, but that's a capital X. And here what this statement says is the probability that our random variable equals a certain value of x equals 0. You might say, okay, so that means that no matter what we pick, the probability of picking that is 0. Yeah, okay. And the reason is because this is a continuous distribution, okay? And what that means is that no matter how carefully we measure, our measuring tool is going to have a limit to it. Okay? If you have a thermometer and it measures to the 10th of a degree, okay? If it's, 78.4 degrees, all that tells us is it's somewhere bigger than 77.5 and smaller than 78.5. We have a range, so the likelihood of getting any exact value is 0. Okay?
So even if it measured to the 10th,
yes,
and it was exactly on a 10th,
well,
the probability would still be 0.
That's the thing. We don't know. Yeah. And what we're doing here is we're going to look at intervals. Okay? To find a range, and the reason is because it's continuous. No matter how precise our instrument is, we can never be assured that it's exactly 0.0 or 0.5 because our instrument is rounding somewhere in there. Okay? And I know it's kind of it might seem a little silly, but that's just how it's done because it's continuous. One example, get to that in a second. One example I used is, up in Atlanta, you have the Coke manufacturing plant, which is a really cool place if you've never been there. I was there, yikes, 17 years ago or something like that, or maybe 16 years ago. It's like 99 or something. But it was cool back then. I'm sure it's even better now. But, when they fill up a 20-ounce bottle, not all of those bottles have exactly the same amount, okay? But what you'll have is, if you were to actually go back and measure how much was in each bottle, those measurements would be normally distributed. Okay, the mean would be 20, but maybe something happened and this bottle got, 20.1 ounces and this one got 19.9, and there's a range actually of acceptability. And what manufacturers will do, and I'm sure Coke does this as well, they'll take out random samples and actually measure how much is going in there. And there's a certain tolerance level that's acceptable to still be allowed to legally call it a 20-ounce bottle of pop. Okay? Or soda. You guys call it soda. So weird. Anyways, if you're in Georgia, even if it's Pepsi, everything's called Coke. My sister-in-law is from there. That's even weirder, but it's Georgia for you. But anyways, that happens in a lot of things. There's a certain tolerance level, and the measurements have to be within a certain range. I haven't noticed down here. I know in Ohio the county auditor goes around, not him specifically, but his office goes around and tests all the gasoline pumps, and they'll actually, pump a gallon of gas and then measure it to make sure it's actually a gallon of gas. Okay, because it's going from the pump to your car. How do you know that's actually a gallon of gas? So the government goes around and tests all the pumps to make sure that it's actually measuring things properly. And I don't know what the exact ranges are there, but there is a tolerance level. But if you took all those measurements, the mean would be a gallon. Sometimes you might get a hair more than a gallon, sometimes a hair less than a gallon, but on average, you're getting a gallon of gas. Okay? Now, what we're using in the normal distribution, you do not need to write down the actual function here, but this is a term you ought to be familiar with, is the probability density function, okay, or called a PDF. This is the function for a normal distribution, okay? You may remember, if you did this section in SL1, you may remember under when you were looking at exponential growth models. Do you remember that unit on exponential growth and logarithmic growth? A couple of the other models you had were a logistic growth model, and then one of them was a Gaussian model. Okay, and that was a bell curve. Well, this is the function. Okay, this is a constant, all right? But you'll notice this whole function is dependent on two values. One is mu, which stands for what? What's mu in statistics? Population mean, good, okay? Or what you'll see them call it here is the mean of the distribution. And then the sigma stands for?
Standard deviation.
Standard deviation, okay? Now, when we actually name it, this is something you have to be careful about. When we actually name it, we're going to use the variance, okay? So, notice the notation here. This notation is important because it'll describe data in this way. The random variable x is distributed. That's what the little tilde stands for here. Okay? X is distributed normally, that's what the n stands for, with a given mean and a given variance. Okay? So that's what you'll see. That's what you'll see your data given as. Okay? X is a continuous random variable distributed normally with this mean and this variance. Okay. If you want, you could say like this with mu and sigma squared. Okay? So, how do we sketch these bell curves? Okay? Well, if you had the PDF, you could, or if you could remember this form, you could plug in mu and sigma into it and graph it. Okay? The likelihood of any of us actually remembering that equation is very slim. We're not going to try to memorize it, okay?
So that entire first part raised to that power of that equation.
Actually, just the e is being raised to this power. Yeah. So, yeah, it's not a pretty equation. But what we can do is we can sketch and get a good general idea of certain things, okay? So if we're asked to draw a normal curve, a normal distribution curve, we would start out first of all with an x-axis like this. It doesn't matter really where the y-axis is, unless you're including 0 on there. But here we're given 3 different values that are distributed normally, okay? And what we could say in this case is A is distributed normally with a mean of 25 and a variance of 25. Yeah. Do be careful if you're given it this way. Remember that this second number is variance, so you need to square root it. Okay? B would be distributed normally.
30 coming 4.
Yeah, 30, and the variance would be 4. Okay? And then C is distributed normally with a mean of 21 and a variance of 100. Okay? So that data is very spread out. But let's take a look at how we would sketch. Let's do A. Okay? How would we sketch this? Well, first of all, we would start with our mean. And I'm going to put that right in the middle here. Here's mu. It's at 25. Okay? And it's good to label it both in terms of mu and with the value itself. Okay? So I'm going to put my value here. Now that, on the normal distribution, your mu is your mean, but because the normal distribution is symmetric, that's also your median. Okay, so in the normal distribution, your mean and median are the same thing. Okay? Then, what we're going to do is use our standard deviation, 5, and go to the left and to the right. So 25 minus 5, that's 1 standard deviation below, so I put mu minus sigma, that's going to be 20. And then I come over here to the right, and I do mu plus sigma, and that's 30, okay? And at both of those points, we're going to have about the same probability density, okay? In other words, it's going to be at about the same height at that point. This should be a little closer to the middle. Then we go another standard deviation to the left. We have mu minus 2 sigma, and that's going to be 15. And notice at this point we're going to be much lower. If we go another standard deviation to the left, we're at mu minus 3 sigma, which in this case is 10. And notice we're very low. Okay? There are very few scores out here at 10. Mm-hmm.
So mu would be like 50%, and then 2 standard deviations for mu would be like 25%.
Mu is 50%. We'll get the other percentages actually. It's not like quartiles here. Okay. Now, if we continue going up, here's mu plus 2 standard deviations. That's 35, and then so that's going to be about right there. And then mu plus a 3rd standard deviation is at 40. That's going to be right around there. So we have our bell curve here. I could see. Now notice this does continue in both directions, okay? There's just so few people here that it's hard to see it all, okay? But let's take a look. As Andrew mentioned, this mu is going to be at the 50% point. That's our median score, okay? So if you're asked what's the probability that something lies below the mean, you're going to say 50%. What's the probability that something lies above the mean? That's 50%. Okay? Well, what are some observations that we can make here, other than that? Where's the data in relation to our mean?
Evenly distributed.
Evenly distributed on either side. What else? Where is most of the data? What?
Below it. And on the,
What? When we're talking about below or above, we're talking left or right. Okay. Most of our data is near the mean, right? The further we get away from the mean, the less of our data is going to be out there. Okay, and if you think about things, that makes sense. If we were talking about people's height, most people are, most adult males are somewhere around 6 foot. And the taller you get or the shorter you get, the fewer people you're going to find at that height. Okay? That's why if you're trying to make the NBA, you have a much less of a chance if you're 6'4" than you do if you're 7 foot. Because if you're 7 foot, there's a lot less competition. When I was coaching, the one statement that some other coach made that stuck with me is you can't teach height. Okay? You can teach someone to dribble, you can teach someone to shoot, you can't teach height. So, but that's why if the taller you are, here the distribution would be much lower, so you have less competition. Okay? That's how, people who can only shoot 30% free throws like Shaquille O'Neal can still be, a great basketball player because he's just huge. Okay? But anyways, let's talk about the actual percentages, okay? I mentioned already you can't think of this in terms of quartiles because we're not finding the 25% mark or the 75% mark here, okay? So let's look at this in terms of percentages. Within one standard deviation is approximately 68% of our data, okay? So if I go up to 30 and down to 20, 68% of my data is going to lie in that range. Okay? Now, that means that on either side of this, because this is symmetrical, half of 68 is 34%. So 34% is going to be on this side, and 34% is going to be on this side. Alright? Everyone with me so far? Now, your book does use, I think it's like 68.37% or something like that. The accepted value, even by your book later on in problems and stuff, the accepted number is 68%. Okay? Going out to 2 standard deviations. 2 standard deviations is 95%. Okay? That means 95% of our data is going to be within, in this case, 15 and 35. Okay? So, 95% of our data lies between here and here. Okay? So if you think about it, from 68 to 95, that's another 27%, right? So that means 13.5% is here, and 13.5% is over here. Okay? And I'd recommend, if you're not already, that you write down these percentages, because the likelihood of you remembering them all off the top of your head is not real good. Okay? But again, that's all the data between the mu minus 2 sigma and mu plus 2 sigma. Okay? Then the third standard deviation. This you'll see a little bit of variation. In fact, we're going to look at a little video later and they mention it's 99.7%. Depending on who you read or whatever, some will round it to 99.5, some will say 99.7 or whatever. We'll use 99.5%. But between 10 and 40 is going to be 99.5% of our data. Alright, so if you think about it,
2.25.
you know, yeah, we need 2.25% in each of these tails here. And then that just leaves a 0.5% for everything else. Okay? So beyond 3 standard deviations to the left, that's going to be, you know, 0.25%. And above 3 standard deviations above the mean is going to be the last 0.25%. Okay? But those percentages can be used a lot to get general idea of how many people are going to be in this range. Okay, and we'll actually do some practice with that later on here. Okay. Now, the other thing that I want to mention here is, you know, we have this data for B and C. Okay. And other than the fact that, yeah, B has a mean of 30. So obviously the mean is going to be right here, you know, instead of at 25. But look at your standard deviation. What effect, this is a question I have down here, what effect does the standard deviation have on your curve? Okay? Here we have 2 examples, one with a standard deviation of 2 and one with a standard deviation of 10. How are those going to look different than the one that we just graphed?
Push it together, spread it apart.
Okay, yeah, it's going to push it together, spread it apart. So B, I'll sketch it here. B, with a mean at 30, you know, its mean might be here. Actually, I should make that a little taller. But with a standard deviation of only 2, we're going to be reaching that third standard deviation at 36, which is like right here. Okay? And we're going to be reaching the third standard deviation on the left-hand side at, you know, 24. Okay? So you'll see what effect this has on the bell curve. It's much skinnier. Okay? Which means our data is much more centered. Alright? Whereas, run out of colors here. Go back to black. Alright, with C, the mean is going to be at 21, but notice, with a standard deviation of 10, you know, we're at 31 and then 41. We're not reaching our third standard deviation until way out here. And, you know, here's 11, 1, and -9. You know, here's our bell curve for C. Okay? So you see the effect that this has on our graph. Okay? Are there any questions on sketching these? Okay? We'll get rid of these. There we go. Alright, so I want to sum things up here with a little video. And he does reiterate quite a bit of what I said. He also introduces So as a standard normal distribution, just in brief, and that's what we're going to get to on Thursday. But let's take a quick look at this, and hopefully this will be helpful. Okay.
Let's look at an introduction to the normal distribution, also known as the Gaussian distribution. The normal distribution is an extremely important continuous probability distribution that arises very, very frequently in theory and practice. Here I've plotted out what is approximately the distribution of the height of adult Canadian males. And this, what we see here, is a normal distribution. This is our variable down here, and f of x is what we call the probability density function, which gives the height of the curve at point x. Here's the equation for the probability density function of the normal distribution. We're not going to be working with this directly very often, but there's a few points we should note. First of all, if the random variable x has a normal distribution, then it can take on any finite value. There are two parameters to this distribution. Mu is the mean of the distribution, and the mean can take on any finite value as well. Sigma is the standard deviation, and sigma squared, of course, is the variance. Sigma has to be some positive value, and of course, sigma squared would have to be some positive value as well. Here's a normal distribution plotted out. Mu, the mean, is also right smack dab in the middle of the distribution. The distribution is symmetric about mu. So mu represents the mean of the probability distribution, and it's also the median of the probability distribution. Now let's try and get some perspective for what sigma represents. Here I've plotted in one standard deviation below the mean to one standard deviation above the mean. And as we'll see a little bit later on, this area between one standard deviation below to one standard deviation above is approximately 0.68. 68% of the area lies within one standard deviation of the mean. Here I've plotted in mu minus 2 standard deviations to mu plus 2 standard deviations. And approximately 95% of the area lies within 2 standard deviations of the mean. And approximately 99.7% of the area lies within 3 standard deviations of the mean. Here's another plot to give us a little perspective on what sigma represents. Over here, this red line represents a normal distribution with a standard deviation of sigma 2. And this white curve represents a normal distribution with a standard deviation of sigma 1. But sigma 2 is double sigma 1. So the standard deviation on the red curve is double the standard deviation of the white curve. And we can see that when the standard deviation is greater, there is more area in the tails and a lower peak. There are an infinite number of different normal distributions, corresponding to all the different possible values for mu and sigma. If x is a random variable that has a normal distribution with mean mu and variance sigma squared, we write this as the random variable x is distributed normally with a mean of mu and a variance of sigma squared. X is distributed normally, a big N. First term is the mean, second term is the variance. Be a bit careful here, as different sources can have a different term in here. Sometimes people have the second term representing the standard deviation. I have the second term representing the variance. So just be a bit careful with that. By definition, the standard normal distribution is a normal distribution with a mean of 0 and a variance of 1. We often represent random variables that have the standard normal distribution with the letter Z. And yes, I am Canadian. And this, we might say, if Z has a standard normal distribution, we might write this as Z is distributed normally with a mean of 0 and a variance of 1. that being mu, that being sigma squared. And if the variance is 1, of course sigma is 1 as well. As we will soon see, we very often need to find areas under the standard normal curve. Probabilities are simply areas under the curve, and very often the question of interest involves finding a probability. Finding probabilities and percentiles for the normal distribution requires integrating the probability density function. There isn't a closed form solution, and it must be integrated numerically. Fortunately for us, we're going to use software or a standard normal table to actually find these values in practice.
All right, so he does reiterate a bit of what we said already, but he also kind of introduces that concept of the standard normal. The idea there is that we're taking data that we have, and rather than expressing it as its actual values, we're expressing it as a distance away from the mean in terms of the standard deviation. So one standard deviation has a standard normal value of 1, and so on. Yes?
So when you say like a variable has a normal distribution, that's just a way of saying that naturally the data is symmetrical.
It's symmetrical, and the majority's in the middle. It's possible to be symmetrical.
That's just the assumptions like base this graph off of, right?
Yes.
Okay.
Yes. It is possible to be symmetrical and not be normal. Like this technically is symmetrical, but
Yes.
normal meaning that your mean and your median are the same, and it all trends towards that bell curve. So. All right, so let's practice with a little bit. Take a couple minutes here. And we're actually going to get a couple from the homework done, so that'll be nice. But here we have the mean height of players in a basketball competition is 184 centimeters. If the standard deviation is 5 centimeters, what percentage of them are likely to be in these different ranges? Okay? The first thing I want you to do, and we'll kind of talk through these first of all, or we will talk through these, but before we talk about it, I want you to make a sketch of the standard or of the normal curve for this data. Okay? So the mean is 184, standard deviation is 5. Okay? So go ahead, get out some paper, make a sketch of the standard normal or of the normal curve. I'm saying standard every time. Get some paper, sketch it.
It was 22 when I said it was at 27, so I thought it was actually 22 at 27.
Just the same percentage, right?
It's the same percentage, yeah, but it was basically like you got 3 out of 3 on a problem and I didn't give you credit for it, so it's actually a higher percentage, same number of points off,
Right.
but a higher percentage. So.
So, Mr. King, will we be having another quiz or a test before the trimester ends, or?
Next Tuesday is our big test on all of the statistics and stuff that we've done.
Oh, okay, but not this, right?
Yes,
Oh,
that's,
this?
everything we do this week will be on our test next Tuesday.
Can you upload
Wednesday.
all your like
Wednesday.
They're on,
chapter stuff? Are they up on
Yeah.
the website?
yeah,
Okay.
go under SL2 notes. So. All right, what's mu here? Mu's 184. Okay. And then if I go to mu plus sigma, I'm at mu plus sigma is at 189. Mu plus 2 sigma is 194.
How do you get those?
We're just adding
Oh,
standard
Oh, okay.
deviation of 5.
you just square.
Okay,
Why do you write u plus 0 instead of?
that's a sigma. I'm sorry.
Sigma. Sorry.
Yeah, that's okay. And then the last one we'll go out to is mu plus a 3 sigma,
204.
and
Oh, wait.
will just be
189.
199. Yeah. Okay. So what we can do, we've got our bell curve here, and as long as you get a decent bell shape, okay, you know, you should get a somewhat of a bell shape there, right? So that gives us an idea here. Then we go to the left, mu minus sigma. What do we get?
179.
179, okay. Mu minus 2 sigma,
174.
good, 174. And then mu minus 3 sigma, 169, okay. And there's the left side of our bell curve, okay. Now, this is where, when you're doing a problem like this, it would be helpful to write in your percentages, okay? So let's actually, we know there's 34% on either side of our mean within 1 standard deviation. And then how much in these ranges? Yeah, 13.5%. And then how much between the second and third standard deviation?
2.25?
Yeah, 2.25. And between this, same thing. And then past 3 standard deviations, we've got that last 0.25% on either side. Okay? Alright, so any questions on that? How we labeled all those? Alright, so now we look at our different questions. How many are taller, or what percent are taller than 189 centimeters? We're going to come over here to 189, and then what percent is to the right of that? 16%. This is 2.5, 2.5 plus 3.5 would be 16%. Okay? Alright.
84.
Then for B, taller than 179 centimeters,
84.
84%. Okay? Again, we're going to the right. That's 84%. Now, one thing I'll point out with this question, okay? How much is to the left of 179?
16.
16. Notice this was mu minus sigma all the way to the left. Mu plus sigma all to the right was 16%, right? Here's where you can use the symmetry to make things a little easier on yourself if you want. If this is 16% here, then this over here is going to be 16% as well. and 100 minus 16 is 84%. That's what's called the complement principle. All these percentages have to add up to 100%. Okay, we're talking about probabilities, right? So probability, everything has to add up to 100%. So if this is 16 to the left, we know 84 has to go to the right. Right? See, part C, between 174 and 199. So
97,
from here to here, what'd you get?
95, 97.5.
Okay. We've got 2 1/4 plus a quarter, that's 2 1/2, right? Plus another quarter, so that's 2 3/4%. So this would be 97.25, right? Okay. Or we can add up the middle, all right? You guys know, and this might have been easier, right? If we go from -2 standard deviations to +2 standard deviations, so what percent is that? From -2 to +2?
95.
95, and then we just added on this extra 2 1/4, right? So 97 1/4. And then lastly, D. How many are over 199 centimeters tall?
99.
Yeah, that's just 0.25%.
Yeah, almost.
It's just the opposite.
It's like 96.
It's just the opposite.
You got the compliment. Alright, so 0.25%. Now, what do all these percentages mean? These mean that if you were to pick some random player out of this tournament, then you have a 16% chance that they're going to be taller than 189 centimeters. Okay? And so on. That's what those percentages mean. Remember, these are probabilities. We'll look at that more tomorrow.